The person online, can you confirm if you can hear me clearly? The person online.
We can hear you.
Thank you so much. Okay, so good morning, everyone. I want to welcome you back from spring break. I hope you're enjoying your break. Today, we're gonna start what I call multidimensional scaling. For those of you who are actually working in this area, for your project, please pay attention. Okay. We call this MDS, or multidimensional scaling. And of course, my TA will walk you through how to implement this in now. So I want to welcome you to multidimensional scaling, an ISO map, okay? In the outline, I'll quickly have a review on PCA and sparse PCA, because the PCA actually has a connection to MDS. So, and that's why I'm going to start from there. I'm going to introduce you to MDS and, of course, how to implement this in R, then also walk you with applications. So let's have a quick review on PCA and sparse PCA. And let's see how these are connected to MDS. Of course, before now, if you are interested in reducing dimensionality, maybe you got a lot of features and you're working with unsupervised learning. Unsupervised learning mean, maybe you do not necessarily have response variable, you do not have an outcome variable, you only have your data X, and you got a lot of features, okay? And your intention is to reduce the dimensionality, okay, by artificially fabricating what I call dimensions, a fewer dimensions. Of course, we make use of principal component analysis. Of course, I walk you through that the other time, okay, and when you get your principal component analysis, there's going to be what we call loadings. Okay, the loadings are the eigenvectors that correspond to the largest eigenvalue. Now, the loadings may be dense in the sense that they are all non zeros. They are all non-zeros, and it may be difficult for you to interpret when there's a dense in the loadings, and that was why we try to sparse. Okay, the sparsity is to shrink, some loadings, loadings that are very, very weak. You actually shrink them to zero. That's what we call sparse or PCA, so that your loadings become more interpretable. That is why you do that. Okay, and I remember I actually said that situation where uh, we got some correlated variables, and using uh, when you shrink to zero, shrinking loadings to zero is like we are using lasso penalty. The lasso penalty is actually going to shrink unimportant variable, the loadings corresponding to irrelevant variables to zero. But situation where you have where variables correlate, lasso penalty will struggle. Okay, your result will be unstable, and that is why, in addition to using lasso penalty, you also use a ridge penalty, and that will come in form of an elastic net. The elastic net is when you have a transition, between the lasso penalty and the ridge. So that's our intention with the PCA and the sparse PCA. But let me tell you this situation where I'm not working with distance, because in the you before I can use the PCA, of course, my I have to have an input matrix, data matrix that are not necessarily distance. Okay, not distance between this maybe this city or that city or distance between that and that. We have variables that are on their own. Maybe you're talking about um maybe one of the variable. I remember the other time when I walk you through this, we use a sports variable like 100 meter, 200 meter, and so on like that. So, 100 meter and 200 meter is not a that is not talking about distance between 100 and 200. Okay. Now, situation where we have an input variable, please pay attention. And the input variables that we have, okay, they are actually distance between that and that. Okay, maybe distance between European city or the distance between American cities, or you want to talk about distance between samples of genes. So we actually going to make use of MDS if we want to reduce dimension. Let me tell you this. Whether principal component analysis or MDS, the two of them are dimensionality reduction technique, except that the difference between them is that the PCA, we apply that, on, or, we don't apply that on a distance matrix. We apply that on a data matrix, okay? And from the data matrix, or maybe you get your covariance matrix, or you get your correlation matrix, and you now apply the PCA, okay? But MDS, it has to be the input matrix have to be a distance matrix. So if I have a distance matrix, okay, if I have distance matrix, and my intention is I want to generate a coordinate in a way that I want to project, okay, the distance, the observations, okay, in a higher dimensional space into lower dimensional space, okay, and in such a way that I want to preserve the original distance in the higher dimensional space, in a lower dimensional space, then I'm actually going to be doing MDS. Okay, so I want to welcome you to multidimensional scaling that we call MDS. Okay, this MDS are also another dimensionality reduction technique like PCA, except that the input matrix have to be a distance. I'm sorry, yeah, it has to be a distance matrix. Now, for better understanding, I think this is a recap this is a recap on PCA. Okay, PCA also is about dimension reduction, and of course, in PCA, you know what we're interested in. Okay, we actually the interesting direction we in the data according to the PCA criteria, the one that captured the largest variance in the data. Okay, and of course, the PCA is about variance maximization. Okay. So and another thing is PCA is a linear reduction method. We are assuming that there's a linear combination between the artificial fabricated dimensions, the fewer dimensions that we create, and the original features. Okay, so it's also a way of projecting from the higher dimension to lower dimension, except that we're not working with a distance matrix. Now, this is the goal in the MDS, okay? To find a multidimensional geometric representation. Let me tell you this. The way the data is in their natural distance, okay? Not in a geometric representation. And if in a geometric representation, it will be very easy to see. If I'm talking about distance between cities, okay? The way it is originally, you may not be able to know those cities that are that are clustered, or you may not be able to know those cities that are far apart. You may not be able to know those cities that are actually close together, but not until we have a geometric representation. The geometric representation is more or less going to be like a map, okay? And it will be very easy for you to view that, okay? And that is what that is the goal of the MDS. Okay, we actually want to reflect that same relationship that the objects have in their original higher dimensional space. We want to reproduce that same relationship in a lower dimensional space. And let me tell you, The difference this have with the PCA is the input data. In the PCA, the input data, so that you use a covariance matrix or you use a correlation matrix, depending on whether the units of measurement are the same or not. But in the case of MDA, we don't need that. We need a dissimilarity matrix. Please pay attention. Dissimilarity. Dissimilarity means distance matrix. That's exactly what I mean. Okay, that is the input. But let me tell you this: the intention here. Please pay attention. Oh, let me see if I'm going to use this. Okay, so the intention here is actually the question is, if I have a distance matrix, one of the example that I'm actually going to cite is the using the European cities. If I have a distance matrix, okay, involving European cities, maybe London, Paris, Dublin, Warsaw, and so on like that, I do not necessarily need to see European map before I will be able to view that efficiently. I can use an MDS. But what MDS is going to do is the MDS is going to generate what I call a coordinate, because if I want to place something on a map, I need a coordinate. Okay, it's actually going to generate, you're going to find coordinate. That coordinate is what I call Z1 up to Zn. It's just like I have an object, X1 up to Xn. The object may be countries. Okay, and what I want to do, I want to generate, okay, for each object, I want to generate a coordinate. And that very coordinate may be in a two-dimension because, oh, we normally want a 2D or 3D. If it is two-dimension, it means I'm actually going to have SY. X-axis, Y-axis for each of these objects. Okay, that's what I call Z1, Z1, Z2, up to Zn, and such that the Euclidean distances between them, is as close as the dissimilarity that we observe in the original I-dimensional space. Okay, so that is our intention here. Now, the application, just like PCA, is also a dimensionality reduction technique. And for effective visualization, it is when we have a 2D or 3D. When you imagine I have so many features, higher dimension, but I just want to put it down to 2D or 3D. Of course, I'm actually going to use the idea of MDS, provided, that the input matrix is actually a dissimilarity matrix. This is very popular in psychometrics in the field of psychology. I think I gave some example when you want to talk about psychological similarity score. Okay, if you want to talk about survey rating, maybe survey rating of products by customers. Okay, or I want to talk about gene expression similarity. Okay, where I have maybe I have 62 samples and with thousands of gene expression, and I actually want to cluster the patient, but there's a lot of dimensions. The idea of MDS can actually be used. Okay. Now, what I want to talk about now, because of the fact that the input matrix has to be a dissimilarity matrix. So now I want to walk you through different kind of dissimilarity measure. But before I'm going to talk about different types of dissimilarity measure that we use in the MDS, okay, I'm actually going to for demonstrate this. Let's say, for instance, I want to look at the distance between. Let's take a look at this. From Minneapolis, we are in Minneapolis right now. From Minneapolis to Chicago, approximately, we have 400 miles. Okay, from Minneapolis to Denver in Colorado. Okay, Minneapolis to Denver. okay, in Colorado, nine, maybe 900 miles from Chicago to Denver, okay, 1,000 miles. Please pay attention. I got three objects here. The way this is going to come, the way the data is going to come, the data is going to come in form of a distance matrix that is going to be n by n. Please pay attention. If I want to put this in a distance matrix, I'm actually going to have let me be using M for Minneapolis, C for Chicago, and D for Denver. So I'm also going to write M, C, D. I'm going to have this. Please pay attention. Okay, pay attention. I'm actually going to have this. I want to generate the similarity from oh my God, from Minneapolis to Minneapolis, that would be 0, right? From Chicago to Chicago, 0, right? Provided I'm going to the same spots in Chicago, okay? From Denver to Denver is 0. In the dissimilarity matrix, the diagonal have to be 0, 0, 0, because we're talking about distance between the same city. Now, from Minneapolis to Chicago, 400 miles. From Minneapolis to Denver, 900. From Chicago to Minneapolis, 400. From Chicago to Denver, okay, 1,000. Okay, from Denver back to Minneapolis, there's Denver to Minneapolis, 900. Okay, and from Denver to Chicago is 1,000. Now, this is what you're going to see. This is a distance matrix. This is the dissimilarity matrix. But if somebody give you this kind of table, it will be difficult for you to know which cities are very close and which are very far. This is just for 3 cities. Imagine we have thousands of cities. You're gonna be overwhelmed, with that. And in this kind of situation, we need an MDS. Okay. Now, you know what MDS is going to do? If I actually want to do something here, let me just show you the manual way, what MDS is going to do. Let's say, for instance, I actually want to use a 2D. The MDS is going to find coordinate X and Y for each of the city. Coordinate. So I'm going to have a Z1, Z2, Z3. So what is going to do is, if you want to start, it's going to start by putting Minneapolis at the origin. I can put Minneapolis at origin 0, 0. Don't forget the coordinate is X and Y because actually I want a 2D. Now, now you put Chicago on the X axis. You put Chicago on the X axis. If I want to put Chicago on the X axis, okay, 400, 0. Now, if you take a look at this, please pay attention. If you really want to know whether this is correct, you can try to look at the Euclidean distance between Minneapolis and Chicago, which is Euclidean distance. It's actually going to say the X here minus the X here squared, which is going to be 400 minus 0 squared plus 0 minus 0 squared. So that distance is still going to be 400. That is what we mean by preserving we want the Euclidean distance to preserve the original distance in the higher dimensional space. Okay, so now, if this one is for Minneapolis, this is for Chicago, please pay attention. I've seen a lot of exam question here. Now, I now want to get for Denver's. I want to get a coordinate for Denver's. For simplicity, I started with Minneapolis. I put Minneapolis City in Minnesota, 0, 0. And of course, Chicago, 400, 0. And when I find the Euclidean distance, it's still 400. And I want to figure out how the coordinate for Denver. Now, to figure out how the coordinate for Denver, please pay attention. Okay, pay attention. Now I want to figure out. Oh, give me 1 second. I think it's getting. Like I said, pay attention. You don't understand? Ask me. Okay. Now I want to get for Denver's. I want to get a coordinate for Denver's. Without coordinates, I may not be able to put them on a map. I may not be able to have a geometric representation. Now, uh, if I'm gonna do so, I'm actually. What is the distance from maybe Minneapolis to Denver's? The distance from Chicago to Denver's, because I actually want to figure out the coordinate for Denver. Okay, I need to understand the distance from Minneapolis to Denver's, and the distance from Minneapolis to Denver is actually put at 900, and Chicago to that is put as 1,000 miles. Okay, so what I'm actually going to do is, okay, uh, so what I'm actually going to do if I want to find that very distance, so if you're considering this guy now, okay, now Minneapolis and that, Minneapolis 0, okay, so Minneapolis and that, so actually going to be x minus 0 squared, okay, plus y minus 0 squared equal to 900 squared. I'm actually calling that equation 1, okay? Don't forget, Minneapolis is actually, maybe, okay, let me do this so that you don't, maybe I should put, since I'm focusing on Denver's, let me say Denver's Minneapolis and Denver's Chicago. So it's the same. Now you know where the 0, 0 come from, because I put Minneapolis at 0, 0 at origin. Okay. Now I'm gonna do the distance from Denver to Chicago. So now if you take a look at this, okay. So this is gonna be S minus 400 squared, Y minus 0 squared equal 1,000 squared. This is equation 2. What I'm going to do, I need to solve these two equations simultaneously to be able to get the x and y. Now, if you get the x and y, you have to make sure uh, whatever x and y you get, you confirm whether the distance is still that and the distance between that is still that to be able to know. Now, this is a manual way. Imagine if I have 1,000 cities, thousand number of cities. This is going to waste time. What I'm doing now, but this may be part of the test. Better pay attention to that. Okay, now, because of the fact that we're going to be making use of the similarity measures, and I want to walk you in MDS, I want to walk you through different type of the similarity measure. The whole thing start from Minkowski distance. Take a look at this. This Minkowski distance. Minkowski distance is a general form of the dissimilarity measure that we have. When Q equal to 2. We have equilibrium. When Q in Minkowski equal to 2, you have equilibrium. When Q equal to 1, you have a Manhattan distance. And when Q tends to infinity, then you have that. So this is just to tell you, we have different kind of distance. Okay. Now, we also have Mayer-Alanobi distance. The Mayer-Alanobi distance is very useful in classification. Okay. So I just wanted to pay attention to that. Now, these are the distance, these are the similarity measure. We also have similarity measure. Let me tell you this. Why do I need similarity measure? Because I can get the similarity from similarity. I'm going to say that again. Yeah, at times if I'm on similarity, okay, and I want to get the similarity, I can actually get the similarity from similarity. But what are the similarity measure we have? We have a cosine measure. That's a cosine measure. Okay. We have a correlation coefficient. We have a Jaccard Tanimoto coefficient. These are all similarity measures. Okay. I'm just walking you through all of that. Okay. Now, more on the similarity measure. I said here that note that these similarity measures are not always positive, which means they can be negative. Imagine I'm talking about correlation. Correlation can be negative. Just wanted to take note of that. Okay, now I think I'm gonna move away from that. I said something the other time that what I need, the input matrix that I need, is actually dissimilarity. But if my data is in similarity, what efforts am I going to put in place to convert similarity to dissimilarity? This is what I'm trying to do here. Please pay attention. Converting similarity into dissimilarity because your data could come in form of a similarity. When I have a similarity, I can actually convert that to dissimilarity. The very first way to do that, okay? If I'm giving a similarity measure, okay, how do I determine a dissimilarity? I can do that. Look at that. Data ij is the similarity. The similarity means the distance between object I and object j. That's why you see data ij. The distance between object I and object j. If I know the similarity between them, and I want to find if this is the similarity, okay, when I subtract similarity from a particular constant, then I have a dissimilarity. Please pay attention. Let's say, for instance, I'm talking about correlation now. If Sij is a correlation between objects, let me tell you this. When a correlation between two objects is very high, then they are very close. They are similar. They will be more similar when the correlation is very high. That's what it means. Take a look at this. Take a look at this. Here, do you know that if I use a constant 1 minus Sij, where Sij is a correlation, that will give me a dissimilarity. And I said something the other time, similarity measure can be negative, correlation can be negative. I need to find an absolute value before I subtract from 1. Does that make sense? Now we also have different kind of ways of getting the similarity measure. That's another one. Okay. Now this one comes with parameter alpha. Okay. And which can be this or that, where the alpha and the sigma, they're going to be viewed as a turning parameter. And I say here, the larger alpha, okay, the smaller sigma, the faster the similarity approaches 0. When the similarity approaches 0, the similarity will actually going to be huge. When the similarity is getting smaller, the similarity will be getting bigger. Because similarity and dissimilarity, they are mutually exclusive. Does that make sense? It's another form of getting the similarity. Okay. So this, what I just presented to you here, is a way to convert similarity into dissimilarity. And why do we need that conversion? We actually need that conversion because we want to work with dissimilarity. The MDS work on dissimilarity. Okay, let me tell you this. When you're talking about dissimilarity, it depends on the measurement scale. The one that I was talking about the other time when I was talking about the distance matrix, may actually have to do with maybe a quantity, a quantitative variable. We could work on ordinal. It could be categorical. It doesn't matter. Okay, so I just want to tell you we can find similarity and dissimilarity of different kind of variables, whether categorical, whether ordinal. We can even have a mixture of that. Okay, and that is why for ordinal, where you rank, we're going to have that. And for categorical, let me tell you this. If x equal to y, okay, if x is the same thing as y, okay, then the dissimilarity is 0. Dissimilar. That means they do not have any dissimilarity. They are all perfectly similar. That is what this guy is trying to say. Okay. So if S equal to Y, it is zero. But what if in a situation where S is not equal to one, equal to Y? If two variables are not the same, then we're going to code that. We're talking about coding, categorical, variable. It's either two variables are similar or not. If they are similar, we're going to code that as one, I'm at zero. If they are not, we're going to code that as one. Okay, I'm going to say that again. If they are similar, we're going to code it as zero, which means there's no difference. Okay, and if they are not similar, then we're going to code it as one. Okay, I'm moving now. Now take a look at this. This is a combining similar. Now we can actually combine. Let's say for instance we have different kind of similarity measure. We can combine because at times a particular similarity measure may not do a great job until we combine with another similarity measure. And we also have possibility a particular dissimilarity measure may not do a great job on its own until it is combined with the other dissimilarity measure. And that is what I'm trying to say here. Okay. Situation where many data set have mixed variables. At times you could have combination of variables. Could be some are categorical, some are ordinal, some are numerical, and the approach that we're actually going to use will be a weighted average approach. Now take a look at this. Here we're trying to define the distance between X and Y. Okay. And the distance between X and Y, but the variables here some are one is categorical, the other one is ordinal or numerical, and we call this a Goa distance. Okay, call it a Goa distance, and in case there's a missing data, please pay attention. Allowing WK, okay, to depend on the data can handle missing data by setting WK to zero. At times we can also have issue with missing data. But you know what? I think I've dwelled a lot on different kind of measures, this type of dissimilarity measure or similarity measure. I will convert from from similarity to dissimilarity, and how we combine similarities and how we combine the similarity. Let's go back to MDS. We want to go back to MDS. Please pay attention. The major goal in the MDS is the dimensionality reduction, but except that we're working with distance. Take a look at this. I have European cities. I have Athens in Greece, Berlin in Germany, Dublin in Ireland, London in England, Madrid in Spain, Paris in France, Rome in Italy, and Warsaw in Poland. And as you can see here, this is actually the distance matrix that we have, just like the same way. Now, if you have this distance matrix, this is a dissimilarity matrix. If you take a look at this, it may be difficult for us to see these, cities, European cities that are very close in terms of distance, and European cities that are very far. Okay, we're actually going to spend a lot of effort to be able to see using this. And what we need, the MDS can actually enable us to have what I call a geometric representation of this in 2D or 3D. All what we just need is to get the coordinates. Well, what I was finding the other time manually, Arrow can do that for us in case we have so many cities. Please pay attention. Do you know that using the MDS, this is just trying to say using the MDS. Look at the code. Using the MDS where I only want two dimensions. Initially, there are several dimensions in this data set. And you can now see, oh my God, on the map, you can see it on the map, Dublin, London, and Paris are very close. And you can see Warsaw in Poland and Berlin In Germany, they are very close. And you can see Madrid is far from Warsaw. Madrid in Spain, far from Warsaw. In Poland, do you know that having projected this on a lower dimensional space using the MDS, okay, we are able to see, we do not necessarily need an European map here. We do not need a European map to be able to see whether they are close. The MDS can do the job. How many of you are working on MDS in your project in this class? How many on MDS? Okay, I hope you listen carefully, right? There's of you working on MDS, and everyone listen carefully for the purpose of midterm too. Everybody else. Now you can see now, this is using MDS1 and MDS2, similar to principal component 1, principal component 2. Okay, now I said the original travel distances are not Euclidean, but we approximate them with equilibrium distances on the reconstructed map. Let me tell you this. Initially, the original distances between the European cities, they were not Euclidean. These are natural distance in terms of maybe miles or kilo, whatever. So this is the natural one. This is not Euclidean. But we are the one that actually, for the purpose of projecting this in a lower dimensional space for easy visualization. Of course, we need to be able to generate coordinate, and when you generate a coordinate, you're actually going to use the idea of Euclidean distance. So, situation. But let me tell you this: you well, we may not, the Euclidean distance may not perfectly match the original distance, not perfectly match, and that is why we are approximating. We just want to make sure the distance between Dublin in Ireland and the London in the United Kingdom, in the original, the similarity matrix should be also very close to that distance when they are projected in the lower dimensional space. That's what I mean. Okay, now I'm actually moving now. Uh, Aside, beyond distance in the European city, you can also use this in gene expression data. For imagine you have a 62 lymphoma samples, the 62 individuals, each having 4,000 gene expressions. Okay, and what is the conventional approach that we use before the MDS is heat map. If you take a look at this heat map, this is the conventional approach we used before MDS. You could be overwhelmed, with this. The blue one actually showing the correlation, the higher, the positive or zero, the positive correlation, while the red one is the negative correlation. Somebody that is not in statistics may find it difficult interpreting what we have here. This is the traditional way. I'm expecting those who are working on the MDS project to discuss this. Oh, this is the one of the, this is, when you review the literature, this is the gap. Like, this is the weakness of an heat map, and that is why we need that MDS, that will enable us to do this projection in just with 2D, and which is, take a look at that. Take a look at what I have now. Do you know that using the MDS, the 62 samples of genes, all of this, represent the samples of genes that I talk about. Now, what kind of dissimilarity measure we're using here? We're using the dissimilarity measure. You know what happened? We four of us find correlation. Correlation is a similarity measure. And I told you the other time we can get the similarity from similarity. Now, if your similarity is correlation, just do one minus that. So one minus that becomes dissimilarity. So we project, we now use our two MDS. Okay, we project them, and of course you can see these samples of gene cluster together. That's our intention. We actually want to see those samples of genes that behave the same way, that have the same gene expression. That's exactly what we want to see. Now I'm moving now. Now, let me tell you this. We have three types of MDS. We have the classical MDS, We have the metric and the MDS. We have isomer. I'm going to say that again. We got three types of MDS. We have the classical MDS, we have the metric MDS, and we have the isomer. Now all the one I've been discussing all this why is just the classic MDS. Now, in the classic, please pay attention now. In this classic, we're actually going to start with a dissimilarity matrix. Like I represent the similarity matrix. And you know what? We want to find a coordinate. Don't forget to be able to have a geometric representation. We need to find a coordinate Z. Okay. And after getting the coordinate Z, such that we actually, oh my God, if you take a look at what I have here now, what are we trying to say? Okay, we are actually looking for a particular coordinate in such a way that we are able to minimize the distance between two objects in an higher dimensional space and the lower dimensional space, which means you want to minimize the distance between the dissimilarity, original dissimilarity, and the equilibrium. We want to minimize the distance. That's what this equation one is actually talking about. Now, now that is what but you know what? How do I get Z coordinates? Please pay attention. How do I get this Z coordinate? We believe that when we decompose a particular matrix B, that Z coordinate is going to come from there. Please pay attention. The other time we did matrix decomposition, where is the Z coordinate? Without Z coordinate, there's no way I'm actually going to have a geometric representation. Now, where will the Z come from? We believe that the Z is going to come from the decomposition of a particular matrix B. But you know what? How is matrix B formed? Because we have to form a matrix B, and after forming a matrix B, then we're going to have a matrix B decompose to be able to find the coordinate. Now, I want to show you how the matrix B is being, oh my God, take a look at this. The matrix B is being formed that way. What is A? Look at that. A is the combination of your dissimilarity matrix. The lambda here, if you take a look at the data here, is the dissimilarity matrix. When I multiply the similarity matrix by the similarity matrix and I multiply by negative half, that will give me A. Okay, if I have A, then what about H? H is actually a centered, look at that. That is centered matrix. Okay, and if I use that here, I'm actually going to get my B. And the moment I get my B, then the Eigen decomposition, please pay attention now. The Eigen decomposition of B is going to give me this. Okay, when the Eigen decomposition of B give me that, then it is the same thing as this. Then I will be able to have my Z. And what is my Z now? My Z in terms of the Eigen decomposition is equal to that. If you don't understand, ask me question. We're doing the composition now. We want to have access to the coordinates. Okay, that is how we get that. Now, actually moving, I just talked about the classical MDS. But let me tell you this. In the classical MDS, there is possibility that the distance may not be Euclidean. I'm going to say that again. How am I going to know the distance is not Euclidean? I remember the other time. After getting the coordinates X and Y for Denver, you're actually going to perform the you're actually going to find this and this to see whether you're going to get that and that. You're going to get the 900 and 1000. If you don't get that, then it is not Euclidean. When it is not Euclidean, then the classical MDS fails. When classical MDS fails, what is it next to consider? We're going to consider a metric MDS. Metric MDS. Now, what metric MDS is just going to do is we actually want to go statistical. Going statistical is we're going to introduce an evaluation criteria where we're going to be minimizing the sum of squared distance. Now, for instance, I said in general, the similarity may not correspond to equilibrium distance. When they don't correspond, I cannot use a classical MDS. And I said a more general approach is to minimize a loss function. Okay. Now, when you are minimizing a loss function, then you are using metric MDS. The metric MDS minimize a loss function. Okay. Now, what loss function are you minimizing? You are the distance between what? The original distance in the data space and the Euclidean distance. You want to minimize that. That's exactly what you're doing. And we have three different type of loss function that can be used. The first one is stress. The second one is sum of square stress, and the third one is strain. Okay, these are very commonly used loss function in metric. Now, let me tell you this. This guy is just the distance, the original distance in the eye of the object in the higher dimensional space. Why this guy is actually the Euclidean distance, like the distance between objects in the lower dimensional space. And of course, you are trying to minimize the sum of square distance here. But if you are working with this is where you are only working on distances. You can also work on square distances when you actually want to show the effect. So you can use any of these three. Okay. But there's a comment here that I said SS stress is similar to S stress, but give more emphasis to larger distances. If you take a look at this, because that was why we're squaring that. You can see we're squaring distances here. We're not squaring here. Do you see that? Okay, so I just wanted to see that. And the strain, we prefer strain at times because we are considering inner products. Okay, and the inner product, we believe that it gives a nested solution. The first two dimension of a three dimension are the same as the two dimension. Okay, so any of that can be used. Okay, now the next question is just like similar to principal component analysis. We want to choose, we may want to choose uh, which, how many MDS, just like in principal component analysis, how many components. Okay, we also want to say the same, do the same here. Do we choose two? Do we choose three, and so on like that? But in the case of principal component analysis, you focus attention on the one that explains the largest variance. But here, we don't talk about the one that explains the largest variance. We are talking about the one that could minimize the unexplained variation. Unexplained variance, unexplained, but PCA variance explained. Now, but we have a Kruskal rule of thumb. Okay, situation. If the unexplained is zero, that's a perfect one. You know what perfect one means? The perfect one means the distance in the higher dimensional space is exactly the distance in the lower dimensional space. That is where you have zero. 2.5% is excellent, 5% is good, and so on like that. Don't forget, this talk about variance on explain. Now, on Wednesday, I'm actually going to start isomap. You know what isomap talk about? Isomap is when I'm no longer talking about straight line. When we take a look at principal component analysis, the classical MDS, the metric MDS, we are still assuming a straight line. What of in a situation where I do not have a linear surface, but I have a curved surface? Then I'm going to use an isomap. So isomap is a dimensionality reduction in a non-linear dimension. And that's what I'm gonna walk you through on Wednesday. Is there anyone do you have a question for me before I go today? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.